Welcome to this worked example of the module waves. In this worked example, we're going to calculate the potential energy in time for a mass suspended on a spring. So here you can see the mass suspended on the spring, and we retract it by a distance a and then release it. As you've seen in the lectures, the equation of motion for this mass on the spring is given by xt is a cosine omega t. Now, if we want to calculate the potential energy, we know we don't have a formula for that. But still, can we find the solution to it? I will show you how we can do that. So for that, we first calculate the kinetic energy at its maximum velocity. Now, as you've seen from the equation of motion, when we set it out at distance a, the mass starts to move, and then it obtains its highest speed at this point when it goes through the equilibrium position. And we can also show that. So if this is the equation of motion, then our speed is given by minus a, and then we take the derivative, this cosine omega t. So first we take the derivative of this argument, so we get an omega, and then of course the derivative of this cosine is minus sine omega t. So this is sine omega t. Now when does this take its maximum? For that we make another derivative. We calculate the acceleration a of t. This is equal to minus a, and then another derivative of this sine omega t function. So we get another multiplication with omega. So we get omega squared, and the sine now becomes again a cosine. Cosine omega t. So now we're going to calculate the maximum velocity, and this occurs when the acceleration, which is the derivative of v, is equal to 0. This happens, of course, when cosine omega t is 0, and this occurs for omega t is equal to pi over 2, 90 degrees, plus n times pi, because of course the solution is periodic. Well, just like take the first one, because it's the most simple. So we take omega t equal to pi over 2 and plug that in to the equation for the velocity, and then we find that the maximum speed is equal to minus a omega sine omega t evaluated for pi over 2, and this is equal to unity. So the maximum speed is minus a omega. Now we can first make an expression for the kinetic energy. Of course you can use your well-known formula for that. The kinetic energy, the maximum kinetic energy is equal to 1/2 times m times v max squared. And this is equal then to 1/2 m a squared omega squared. All right. So now we have one side of the equation, the maximum kinetic energy. There's no potential energy and everything is kinetic. On the other hand, we can think, well, if everything is transferred to potential energy, how would this energy equation look like? And for that, we can use dimension analysis. So let's look at the dimension of kinetic energy. For that, we write in the following way. This has dimensions of, well, first here's the mass, that's kilogram, and then we have speed, which is meters per second, but that's squared. So that's meters squared per second squared. Now, our spring has potential energy, and this potential energy is most probably proportional to the spring constant, right? A stronger spring has more potential energy. Now, the unit of the spring constant, K, is equal to kilogram per second squared. All right, so if we now look at the dimensions of this, we see that if we want to calculate the potential energy, we need something of the order of dimension meter squared. So let's make an educated guess. The potential energy is proportional to the spring constant times x squared. But we don't know yet the proportionality constant. So let's think a little bit further. So we have now the maximum speed at this point, and everything is kinetic energy. But at this point, the speed is 0, and everything is potential energy. So let's evaluate these two together, because the kinetic energy needs to be transferred to potential energy and vice versa. So then we calculate the following. We equilibrate the kinetic energy and the potential energy, which means that 1/2 ma squared omega squared is equal to this proportionality constant alpha k, and then the maximum extension that we put onto the string, which is a squared. Now if we combine it with one last thing, we know for the harmonic oscillator that omega squared is equal to k divided by m. Then we find easily by filling it out that alpha is 1/2. That means the potential energy of the harmonic oscillator is 1/2 k x squared. So now, using these formulas, we have solved the entire potential energy of the harmonic oscillator.